Welcome back to Programming Fluency. This is section 7.4, Bitwise Operators. Every integer you have used is really a row of zeros and ones. Sometimes you need to reach in and flip the individual bits. In this video, you will learn the 6 bitwise operators and use them to pack many yes or no flags into a single number. Let's get started. Every integer you have ever used is really a row of zeros and ones. You have been treating them as numbers, adding and multiplying. But sometimes you need to reach in and flip the individual bits. This is how file permissions, hardware registers, and network protocols really work. Let's learn how. This is the plan. First, bits are switches, and, or, XOR, and not, one bit at a time. Next, shifting. The shift left and shift right operators slide bits to multiply or divide by powers of 2. Then bit flags, packing many yes or no options into one integer. After that, set, test, clear, and toggle, the 4 surgical bit operations. Finally, packing and a classic bug, RGB colors, counting bits, and single ampersand versus double ampersand. Why would you ever care about individual bits? Think about a file on a Unix system. It has 3 permissions: readable, writable, and executable. Each is just a yes or no. You could use 3 separate int variables, but that wastes 12 bytes to store 3 bits of information. Instead, you pack all 3 into a single integer, 1 bit for each permission. The value 5, which is 101 in binary, means readable and executable, but not writable. To add write permission, you flip just 1 bit without disturbing the others. This packing pattern is everywhere. Hardware registers, network headers, graphics options, game state. This is the whole idea in one picture. Think of an integer as a row of switches, each on for 1 or off for 0. The top row is the number A. The second row is the number B. Now we apply the 4 logical operators, 1 bit position at a time. And, written with a single ampersand, turns a bit on only where both A and B are on. Or a single vertical bar turns a bit on where either one is on. XOR, the caret, turns a bit on only where the 2 bits differ. And not the tilde, simply flips every bit of A. Look how each result depends only on the bits stacked above it. Every position is handled independently. That is the essence of bitwise operations. These are the same 4 operations in binary and hex. A is 11001010, which is hex CA. B is 00001111. Hex 0F. Notice B has only its lower 4 bits set. A and B keeps a 1 only where both had a 1, giving hex 0 A. Here B acts as a mask, keeping the low 4 bits of A and zeroing the top. O or B keeps a 1 where either had 1, hex CF. A XOR B keeps a 1 only where they differ, hex C5. And not a flips every bit, turning hex CA into hex 35. Each operator has a job, and tests and clears or sets, XOR toggles, and not builds masks. The last 2 operators are the shifts. On the left, shift left, written with 2 less than signs. Take a equals 5 binary 00000101. Shift left by 1 and every bit moves 1 place left, giving 10. Shift left by 4 gives 80. So shift left by n multiplies by 2 to the n, and the low bits fill with 0. On the right, shift right, 2 greater than signs. Take 80. Shift right by 1 gives 40, by 4 gives 5. So shift right by n divides by 2 to the n. One warning: Always use unsigned types with shifts. Shifting a negative signed value is undefined or implementation defined, and it will surprise you. Now the payoff. A bit flag uses a single bit for one yes or no option. The key trick is that each flag is a power of 2, a value with exactly one bit set. Flag read is 1 shift 2, binary 000000100, the value 4. Flag write is 1 shift 1, the value 2. Flag execute is 1 shift 0, the value 1. The expression 1 shift n always produces a value with only bit n set, so the flags never overlap. With an 8-bit unsigned char, you can store 8 independent flags in a single byte. With a 32-bit int, you get 32. With flags defined, the 4 core operations each use one operator. To set a bit, turn it on, use or equals with the flag. To clear a bit, turn it off, use and equals with the knot of the flag, which makes a mask that is all ones except that one bit. To toggle a bit, flip it, use XOR equals. And to test a bit, use plain and inside and if. The beautiful part is that each operation is surgical. It touches only its one target bit and leaves every other bit in perms exactly as it was. Let's combine all 4 operations, modeling file permissions. We define 3 flags, perm read, perm write, and perm execute. We start with perms equal to 0, no permissions, shown as --. First, perms or equals perm read or perm execute sets both bits at once, giving r-x. Next, war equals perm write adds write, giving rwx, then and equals not perm execute clears execute, leaving rw-. Finally, XOR equals perm write toggles write, and since write was on, it turns off, leaving r-. Each line changes exactly one permission. This is the same sequence, traced bit by bit. Start at 0, binary 000, permissions --. Set read and execute by ORing with 4 and 1, giving binary 101, which is r-x. Set write by ORing with 2, giving 111 rwx. Clear execute by ANDing with not 1, that is 7 and 6, giving 110 rw-. Toggle write by XORing with 2, giving 100 r-. Read down the binary column. Each row differs from the one above it in exactly 1 bit. Shifts and OR let you pack several values into one integer. A classic example is an RGB color. Each channel, red, green, and blue, is 1 byte, 0 to 255. Pack RGB shifts red left by 16, green left by 8, and leaves blue in the lowest byte, then ORs all 3 together. So the 3 channels sit in 3 separate byte positions of one integer. Pack RGB of 255, 128, 0 gives hex FF8000. To pull a channel back out, red of shifts right by 16, then ANDs with hex FF to keep only that byte. This shift and mask pattern is how colors and protocol fields are read and written. Another common task is counting how many bits are set to 1. Count set bits loops over all 32 positions. For each position I, it builds a mask, 1U shifted left by I, which has only bit I set. It ends that mask with N, and if the result is non-zero, bit I was set, so it increments the count. For the value hex A, which is 1010 repeating, exactly half the bits are set, so the answer is 16. Notice the letter U after the 1 U that makes the literal unsigned. Shifting 1 into bit 31 on a signed int is undefined behavior, and the U avoids it. Let's finish with the most dangerous Bitwise bug, confusing single ampersand with double ampersand. You write if flags double ampersand flag red. You meant to test the read bit, but double ampersand is the logical and. It treats both sides as simply true or false. If flags is any non-zero value at all, the whole thing is true, so it prints readable even when the read bit is off. The fix is the single ampersand, the bitwise and. If flags single ampersand flag read isolates the real read bit and is only true when that bit is set. Single ampersand works on bits. Double ampersand works on truth values. They are not the same. Let's recap. Bitwise operators manipulate the individual bits inside an integer. There are 6 of them: AND, OR, XOR, and NOT, which work one bit at a time, plus shift left and shift right. The shifts multiply or divide by powers of 2, and you should always use them on unsigned types. A bit flag is a value with a single bit set. Made with one shift and flags let you pack many yes or no options into one integer. There are 4 surgical operations: set with OR equals, test with AND, clear with AND equals not, and toggle with XOR equals. Each changes exactly one bit. And never forget single ampersand is bitwise, double ampersand is logical, and confusing them causes a silent bug. Next, in Chapter 8, you will allocate memory whose size and lifetime you control at runtime with malloc, calloc, realloc, and free, and build your first linked list.